Welcome one and all to the Math Magic Show. So in this one, what we're going to do is find the value of this line integral. So our field is x comma y, those are its components, and then we're going to integrate this over cosine t sine t, which you might recognize as just the equation of the unit circle. The question is, can we make some preliminary observations to simplify our work? And the answer is yes. So take a look. For example, first what you want to do is just sketch this cosine t sine t. That is just a unit circle after all. So when I sketch that out, roughly it's going to look like this, just to get the idea across. Throw in some axes. So this will be my vertical axis right here, and then this will be my horizontal axis. So this represents this curve, and this curve is oriented this way. In other words, it's as if you were traversing the curve in this direction, because as you might remember, for increasing values of t, cosine t sine t, a point on a unit circle moves according to the direction of those little arrow tips that you see. Now, if you just do a sample plot of x comma y, even in just a few places, you will observe something. So what I mean by that is this. Take a look. For example, imagine that I do a plot of x comma y right here. So imagine that this represents the point 1 comma 0. Our field is x comma y. In other words, our field, I meant to put a 0 there, our field looks like this. X comma y means plug in the x coordinate, and then the y coordinate is 0. So that means that if you were to represent the field at that point using an arrow, that field would pretty much look like this. It's just an arrow that is very specifically perpendicular right there. That's the key idea. This is perpendicular. That means right here this is about 90 degrees. In other words, the dot product here and then between this line is equal to 0. So then when we are, for example, at this point, the field, because it's x comma y, will look like that. And it will be perpendicular to the circle in this position right here, you see? In other words, this dot product, for example, would be again equal to 0. I've shown you only two sample vectors, but in reality you can imagine that it's like that all the way around. In other words, it doesn't matter where you go, you're going to have it so that the vector is perpendicular to the circle. When it's perpendicular to the circle, then that tells you basically that this dot product here is equal to 0. And it's like that all the way around at every single point on the circle, which means just by looking at this geometric kind of approach to it, I can tell that the line integral should have the value 0, precisely for these simple reasons. But nevertheless, let's convince ourselves of the truth of what I've just told you by using a more formal argument. So I'm going to say the following. Integral from 0 to 2 pi, that is so because I'm spinning all the way around the circle, and that's 2 pi. And then I'm going to have this quantity, so f of r of t, and then here you put r prime of t dt. This part here corresponds to f dot, and then this part corresponds to dr. So this part represents a little piece of path along the circle because it's r prime of t multiplied by dt. Logically speaking, this is like a bit of distance that comes from traveling at speed r prime of t multiplied by the time dt. That's why it's dr. It's a little piece of path along the circle. Okay, and then you take the field and you dot it with that little piece of path. So here, in other words, let me emphasize this. At this point, for example, what's happening is this is your field. This is f. And then a little piece of the path you can imagine is this quantity right here. That's a little piece of the path. And then this little piece of path, which I'm going to say do in yellow here, that little piece of path along the circle, that's going to be r prime of t multiplied by dt. Roughly speaking, that's the idea. It's a little piece of, and we'll call that dr, a little piece of path. So then when you form this quantity dr dotted with the vector at that point, with the vector field evaluated at that point, you see that because they're perpendicular, that dot product is equal to 0. So I've shown you this at just, one point, one sample point, but you can imagine something like this happening all the way around the circle everywhere. So let's go back to the integral. That explains the f, that explains the dr, integral from 0 to 2 pi. And f evaluated at rt means the following, that wherever you see x, you replace it with the x component r of t, and the y component of the field, which is y, will be replaced with the y component of r of t, which is sine of t. Like that. This is a way of doing it. And then you're going to dot this with r prime of t. So you have to differentiate r of t. Now remember that our r of t looked like this. It was cosine t and then sine t. So the derivative of cosine t is negative sine t, so you put that here, negative sine t. And then the derivative of sine t is cosine t, so that goes right here. And then you multiply by the dt. So this portion right here, this is r prime of t dt, and this portion is f evaluated at r of t. And now let's carry out the dot product. So from 0 to 2 pi, I will have cosine t times negative sine t applying the dot product. So that's going to give me negative cosine t, sine t. Next one, sine t dotted with the other piece there will give me plus sine t cosine t. And then you have the dt on the outside. And let's stop right here, because as I've been saying this whole time, just by geometric reasoning I can tell that the value of the line integral should be 0. But this is confirmed because take a look. These two terms are opposite. They're the same except different sign, which means that they cancel. And we end up therefore with just the integral from 0 to 2 pi of 0 dt, which is equal to 0. But that's not really surprising for us at this point. Alright, so I find myself at the center of the vector field. Thank you so much for watching. Please leave a like and subscribe. I'll see you in another video.